Impact speed. The purpose of this experiment is to estimate the speed of a falling object as it strikes the ground. These are the required equipment or supplies that you needed. Number 1 is a stopwatch. We use a cell phone as a substitute for a stopwatch. Number 2 is string with a rock tied to one end. Number 3 is object with a large drag coefficient such as leaf or feather. We use feather as reference. Number 4 is styrofoam, plastic foam ball or ping pong ball, tennis ball. We use a styrofoam discussion. The area of a rectangle is its height multiplied by its base. The area of a triangle is its height multiplied by half its base. If the height and base are measured in meters, the area is measured in square meters. Consider the area under a graph of speed versus time. The height represents the speed measured in meters per second, and the base represents time measured in seconds. The area of this patch is the speed times this time, expressed in units of meter per second times seconds, which equals meter. The speed times the time is the distance traveled. The area under a graph of speed versus time represents the distance traveled. This very powerful idea underlies the advanced mathematics called integral calculus. You will investigate the idea that the area under a graph of speed versus time can be used to predict the behavior of objects fallen in the presence of air resistance. If there were no air friction, a falling tennis ball or styrofoam ball would fall at constant acceleration gravity, so its change of speed is final velocity minus initial velocity is equals to acceleration of gravity times time of fall. Proceeding to the procedure of the experiment, step number 1. Your group should choose a strategy to drop a ping pong ball or styrofoam ball and clock its time of fall within 0.1 seconds or better. Consider a long fall drop site, various releasing techniques, and reaction times associated with the timer you use. Step number 2. Devise a method that eliminates as much error as possible to measure the distance the object falls. Step number 3 is submit your plan to your teacher for approval. Step number 4 is measure the height and the falling times for your object using the approved methods of step 1 and 2. Height is equal to how many meters. Actual time of fall is equal to how many seconds. Step number 5 is, using your measured value for the height, calculate the theoretical time of fall for your ball. Remember, this is the time it would take the ball to reach the ground if there were no air resistance. Step number 6. Using an overhead transparency or graph paper, trace figure B leaving out the actual speed versus time curve. Draw one vertical line from the theoretical time of fall for your height up to the theoretical speed versus time line. Draw the other vertical line from the actual time of fall up to the theoretical speed versus time line. Starting from the origin, sketch your approximation for the actual speed versus time curve out to the point where it crosses the actual timeline using the example mentioned in the discussion. The area of your stapled region should be the same as to the cross-hatched region. One possible way to do this is to tape a piece of cardboard to the wall and project your transparency onto it. Trace your two regions onto the cardboard and cut them out. Then measure the mass of the two regions. If their masses are not the same, adjust your actual speed curve and try again. Your approximation is done when the two regions have the same mass. Step number 8. Draw a horizontal line from the upper right corner of your stapled region over to the speed axis. Where it intersects the speed axis is the object's probable impact speed. The analyses are the questions that should be answered upon doing the experimentation. Number 1. Have your teacher overlapped your graph with those of others? How does your actual speed versus time curve compare with theirs? Number 2. What can you say about objects whose speed versus time curves are close to the theoretical speed versus time? Number 4. The equation for distance traveled is distance is equals to velocity times time. In this lab, the distance fallen is the same with or without air friction. How do the average speeds and times compare with and without air friction? Try to use different size symbols such as those used on page 66 of your text. Number 5. If you drop a large leaf from the Empire State Building, what would its speed versus time graph look like? How might it differ from that of a baseball? Number 6. The terminal speed of a falling object is the speed at which it stops accelerating. How could you tell whether an object had reached its terminal speed by glancing at an actual speed versus time graph? Merrily we roll along. The purpose of this experiment is to investigate the relationship between distance and time for a ball rolling down an incline. These are the required equipment or supplies you needed to do this experiment. Number 1 is 2-meter ramp. Number 2 is steel ball bearing or marbles. Number 3 is wood block. Number 4 is a stopwatch. Number 5 is tape. Number 6 is meter stick. And number 7 is protractor. Discussion. Measurement of the motion of a freely falling object is difficult because the speed increases rapidly. In fact, it increases by nearly 10 meters second every second. The distance that the object falls becomes very large very quickly. Galileo slowed down the motion by using inclined planes. The component of gravity acting along the direction of the inclined plane is less than the full force of gravity that acts straight down. So the change of speed happens more slowly and is easier to measure. The less steep the incline, the smaller the acceleration. The physics of free fall can be understood by first considering the motion of a ball on an inclined plane. This experiment will require you to make many timing measurements using a stopwatch or, if available, a computer. If you use a stopwatch, develop good timing techniques so as to minimize errors due to reaction time. Proceeding to the procedure, step number 1 is set up a ramp with the angle of the incline at about 10 degrees to the horizontal as shown in figure A with the 6 equally spaced tape markers. So the step number 2 is divide the ramp's length into 6 equal parts and mark the 6 position on the board with pieces of tape. These positions will be your release points. Suppose your ramp is 200 cm long. Divide 200 cm by 6 to get 33.33 cm per section. Mark your release points every 33.33 cm from the bottom. Place a stopping block at the end of the bottom of the ramp to allow you to hear when the ball reaches the bottom. Step number 3 is use either a stopwatch or a computer to measure the time it takes the ball to roll down the ramp from each of the 6 points. If you use the computer, position one light probe at the release point and the other at the bottom of the ramp. Use a ruler or a pencil to hold the ball at its starting position. Then pull it away quickly parallel to incline to release the ball uniformly. Do several practice runs with the help of your partners to minimize error. Make at least 3 timings from each position and record each time and the average of the 3 times in data table A. Step number 4 is graph your data, plotting distance vertical axis versus average time, the horizontal axis, on an overhead transparency. Use the same scales on the coordinate axis as the other groups in your class so that you can compare results.
Trial 1. Stop. Go. Stop.
Step number 5 is repeat steps 2 to 4 with the incline set at an angle 5 degrees steeper. Record your data in data table B and graph your data as in step number 4. Questions in step number 5. What is acceleration? Does the ball accelerate down the ramp? Cite evidence to defend your answer. Number 3. What happens to the acceleration if the angle of the ramp is increased? Step number 6. Remove the tape marks and place them at 10 cm, 40 cm, and 90 cm. At last is 160 cm from the stopping block. As in figure B, set the incline of the ramp to be about 10 degrees. Step number 7 is measure the time it takes for the ball to roll down the ramp from each of the 4 release positions. Make at least 3 timings from each of the 4 positions and record each average of the 3 times in column 2 of data table C. Step number 8 is graph your data, plotting distance, vertical axis versus time, horizontal axis on an overhead transparency. Use the same coordinate axis as the other groups in your class so that you can compare results. Step number 9 is look at the data in column 2 a little more closely. Notice that the difference between time 2 and time sub 1 is approximately the same as time sub 1 itself. The difference between time sub 3 and time sub 2 is also nearly the same as time sub 1. What about the difference between time sub 4 and time sub 3? Record these 3 time intervals in column 3 of data table C. Step number 10. If your values in column 3 are slightly different from one another, find their average by adding the 4 values and dividing by 4. Do as Galileo did in his famous experiments with inclined planes and call this average time interval 1 natural unit of time. Note that T sub 1 is already listed as 1 natural unit in column 4 of table C. Do you see that T sub 2 will equal more or less 2 units in column 4? Record this, and also T sub 3 and T sub 4 in natural units rounded off to the nearest integer. Column 4 now contains the rolling times as multiples of the natural unit of time. Number 4 question, what happens to the speed of the ball as it rolls down the ramp? Does it increase, decrease, or remain constant? What evidence can you cite to support your answer? Step number 11. Overlay your transparency graph with other groups in your class and compare them. Number 5 question. Do balls of different mass have different acceleration? Step number 12. Investigate more carefully the distances traveled by the rolling ball in Table D. Fill in the blanks of columns 2 and 3 to see the pattern. Number 6 question. What is the relation between the distances traveled and the squares of the first four integers? Step number 13. You are now about to make a very big discovery. So big, in fact, that Galileo is still famous for making it first. Compare the distances with the times in the fourth column of data table C. For example, is t sub 2 is 2 natural time units and the distance rolled in time t sub 2 is 2 squared or 4 times as great as the distance rolled in time t sub 1. Number 7 questions. Is the distance the ball rolls proportional to the square of the natural unit of time? The sizes of your experimental errors may help you appreciate Galileo's genius as an experimenter. Remember, there were no stopwatches 400 years ago. He used a water clock, in which the amount of water that drips through a small opening serves to measure the time. Galileo concluded that the distance is proportional to the square of the time. Step number 14. Repeat steps 6 to 10 with the incline set at an angle of 5 degrees steeper. Record your data in data table E as what is shown. And answer number 8 question. What happens to the acceleration of the ball as the angle of the ramp is increased? Number 9 question. Instead of releasing the ball along the ramp, suppose you simply drop it. It would fall about 5 meters during the first second. How far would it freely fall in 2 seconds, 5 seconds, and 10 seconds? Number 10 question. How do the slopes of the lines in your graph of speed versus time relate to the acceleration of the ball down the ramp? Question number 11. When you determine the speed of the ball with the light probes, were you really determining instantaneous speed? Explain. Question number 12. As the angle of the ramp increased, the acceleration of the ball increased. Do you think there is an upper limit to the acceleration of the ball down the ramp? What is it? Getting pushy. The purpose of this experiment is to investigate the relationship between mass, force, and acceleration, or the variables affecting acceleration. The required equipments and supplies are: number 1 is roller skates or skateboard. We use a swivel chair as a replacement or alternative to illustrate how to do this experiment. Number 2 is a spring balance. Number 3 is a stopwatch. Number 4 is meter stick. And number 5 is tape. Discussion. Most of us have felt the acceleration of a car as it leaves a stop sign or the negative acceleration when it comes to a stop. We hear sportscasters describe a running back as accelerating through the defensive line. In this activity, you will investigate some variables that influence acceleration. The procedure. Step number 1. With pieces of tape, mark positions on the floor at intervals of 0 meter, 5 meter, 10 meter, and 15 meter. The path along the floor should be smooth, straight, and level. Gym areas or hallways work well. Step number 2. A student must put on the skates and stand on the 0 meter mark, which we use a swivel chair. Another student must stand behind the 0 meter mark and hold the skater. The skater holds a spring balanced by its hook. Step number 3. A third student must grasp the other end of the spring balance. As an alternative to the spring balance, we use the meter stick and exert a constant pulling force on the skater when the skater is released. The puller must contain a constant force throughout the distance the skater is pulled. Do not pull harder to get going. Time how long it takes to get to the 5 meter, 10 meter, and 15 meter marks and record this data in the data table A Step number 4. Repeat the experiment twice using different skaters to vary the mass, but keeping the force the same. If the results are inconsistent, the skater may not be holding the skates parallel or may be trying to change direction slightly during the trial. Step number 5 is repeat with the puller remaining a different constant force throughout the distance the skater is pulled, but using the same 3 skaters as well. Record your results in data table B. Proceeding to the analysis. Number 1. Until the time of Galileo, people believed that a constant force is required to produce a constant speed. Do your observations confirm or reject this notion? Number 2. What happens to the speed as you proceed further and further along with measured distances? Number 3. What happens to the rate of increase in speed, the acceleration, as you proceed further and further along the measured distances? Number 4. When the force is the same, how does the acceleration depend upon the mass? Number 5. When the mass of the skater is the same, how does the acceleration depend upon the force? Number 6. Suppose a 3 Newton force is applied to the skater and no movement results. How can this be explained?